All right, let's just dive right into it. If you're an aspiring data scientist or a machine learning engineer, I bet you've hit that massive wall of abstract math jargon at some point. You know the one. Well, today, we are going to smash right through that wall. In this explainer, we're going to take all those incredibly intimidating linear algebra terms and translate them into the practical, highly visual building blocks that actually make statistical models and AI tick.
So here's our roadmap for today. We'll kick things off with the vector mixing recipe, learn how to cut out redundancy, define span and subspace, and finally, we'll build the perfect measuring stick. Let's get right to it. Section 1. The vector mixing recipe. Before we do any complex data analysis, we really just need a collection of vectors and a set of rules for combining them.
And that brings us to our very first major concept, the linear weighted combination. Now, I know it sounds super fancy, but honestly, it simply means taking a set of vectors, multiplying each single one by a scalar number, which basically just acts as a weight, and then adding them all together to produce one single new vector. Really, that's the whole shebang. Scalar vector multiplication followed immediately by addition.
Now, you might be wondering, why should I actually care about this? Well, these linear weighted combinations absolutely aren't just some boring textbook exercise. They are literally the fundamental computational engines powering our modern world. Ever used the least squares algorithm in predictive statistics? Yep, that's a linear combination. Principal components analysis for dimension reduction? Linear combinations. Even the actual architecture of deep learning and artificial neural networks rely heavily on linear weighted combinations of input data.
Hey, for the programmers out there who might be feeling a little intimidated by the algebra, take a look at this Python code. Implementing a linear weighted combination using NumPy requires just a few super simple lines of code. You just define your scalars, define your vector arrays, and boom, multiply and add them together. It is an incredibly powerful concept executed with barely any code at all.
All right, moving on to Section 2, cutting out redundancy. Now that we can successfully mix vectors, how do we spot and eliminate the useless mathematical dead weight?
So here is the absolute crucial point we need to understand: linear dependence. A set of vectors is linearly dependent if you can build at least one vector in that set by using a linear weighted combination of the other vectors in that exact same set. Think of it kind of like this. If you can create vector C just by mixing vector A and vector B together, well, vector C isn't really giving you any new information, is it? It's a total copycat. It's completely redundant, and having that redundancy makes the entire set linearly dependent.
To actually test for this, mathematicians use something called the zeros vector test. The rule here is super strict. If there is absolutely no possible way to linearly combine your vectors to produce a vector of all zeros, well, unless you just cheat and set all your scalar weights to zero, which we obviously don't allow, then your set is linearly independent. You've got yourself a pure, pristine set of tools with zero redundancy. Which brings us to Section 3, Span and Subspace Explained. We have our independent tools ready to go. Now, let's explore the infinite universe of things we can actually build with them.
This brilliantly clears up a classic point of confusion for so many people. We hear span and subspace used interchangeably all the time, but we really need to separate them. Think of span as the verb. It's the actual mechanism, the physical action of combining all possible linearly weighted combinations. Subspace, on the other hand, is the noun. It's the resulting geometric space, that infinite set of vectors you literally just created by spanning.
Let's actually look at this visually to really hammer it home. On the left side here, a single vector spans a 1D subspace. It's just an infinite line. Now on the right, two independent vectors span a full 2D plane. But wait, here's the catch. If that second vector was redundant, meaning it was linearly dependent, it would just lie totally flat on the exact same line as the first one. Adding a redundant vector doesn't magically give you a 2D plane. It leaves you stuck on a 1D line because it adds absolutely no new space to your universe. Crazy, right?
And that brings us to this absolute golden rule. If a vector set is linearly independent, then the dimensionality of the subspace spanned equals the number of vectors in that set. This perfectly confirms that only independent vectors contribute to expanding the dimensions of our data universe. So, one independent vector gives you a line, 2 gives you a plane, 3 gives you a 3D space, and so on.
And here we are at Section 4, the perfect measuring stick. Let's combine literally everything we've learned today to create the ultimate customized tool for our data universe. We call this ultimate tool a basis. Think about this for a second. How far apart are Amsterdam and Tenerife? The answer is roughly 2,000. But 2,000 what? That number is completely meaningless unless we attach a basis unit to it, like miles. Just like you need miles or kilometers to measure physical distance, your data desperately needs a basis to be understood and measured. A basis is basically just a set of rulers used to describe the information in your matrix.
To really see this in action, take a look at the data points shown here. You can actually describe these exact same physical data points with entirely different coordinates depending on which ruler or basis set you choose to use. So if you use the standard Cartesian ruler, basis S, that point has coordinates 3 and 1. But if you switch it up and use the dashed ruler, basis T, that exact same physical dot suddenly has coordinates 1 and 0.
Now, to be a valid measuring stick, a basis has to follow two incredibly strict rules. Rule number 1, it absolutely must span the subspace. In science, you simply cannot measure something that you cannot physically reach. Look at that point floating out there. The dashed line is our 1D subspace. Because the point is floating way out in 2D space, our 1D basis ruler simply cannot reach it, which means it definitely cannot measure it.
And here's rule number 2. Linear independence guarantees unique coordinates. If your basis set had redundant, dependent vectors mixed in, you could technically describe a single point using an infinite number of different coordinate combinations. I mean, imagine asking for the distance to Tenerife and someone tells you it's simultaneously 2,000, 1.5, and a bajillion miles. It would completely ruin the usefulness of the measuring stick. A point must have exactly one unique set of coordinates within a basis, no exceptions.
All right, let's bring this entire explainer together for the grand finale. What mathematically defines a basis? Honestly, it's just the elegant combination of our previous two building blocks. 1, it spans the subspace, meaning it can actually reach all the data you care about. And 2, it is an independent set of vectors which completely guarantees zero redundancy and perfectly unique coordinates.
I want to leave you with this final thought today. When you hear massive buzzwords like principal components analysis, feature extraction, or image compression, just know that they aren't some sort of dark magic. In applied linear algebra and machine learning, a huge part of the job is literally just searching for the optimal set of basis vectors to describe complex data. So I have to ask you, what is the optimal basis for your next data problem? Definitely think about that as you continue your data science journey. Thanks so much for joining me on this explainer, and keep learning.